Recording in progress.
Yeah, let's see. Switch on your cams, everyone. Did anyone try this? See. So now we know the total energy stored in the system is integral. So we saw last time, energy density of even this thing. So this will be E net cos square dV. But what is E net? So this is half epsilon integral. E net is nothing but E1 bar plus E2 bar dV, isn't it? So electric field at any point in the space is E1 plus E2 bar. So if you take the electric field at every point and if you do the integration half epsilon E square, I'll get the total energy of the system. Now if you expand this, you'll end up with half epsilon E1 square plus E2 square plus E1 bar to E1 bar E2 bar dot dV. So this will be half epsilon integral E1 square dV plus integral half epsilon E2 square dV plus epsilon integral E1 bar dot E2 bar dV. Now, if you notice something here, isn't this the self energy? What is half epsilon E1 square? That is the energy due to only the first shell. So if you take only the first shell, then half epsilon E1 square is the self energy of the first shell, which is K Q1 square by 2R1. What is this thing then? This is your self energy of the second shell. Which is K Q2 square by 2R. So in the total energy, what is left? The interaction energy, isn't it? So there are actually three components of energy, two self energies, self energy, and there's an interaction between them. That's your third energy, isn't it? That's your interactional energy. So that's what the third one represents. And what is the interaction energy? Because L is much, much greater than R1, R2, you can treat them as point charges. This will be K, Q1, Q2 by L. Since the distance is very far, they can be treated as point charges. So there, done. So epsilon integral E1 bar dot E2 bar dV is K Q1 Q2 by L. So you want integral E1 bar dot E2 bar dV, just shift that epsilon there and you got an answer. Is that everyone? So E1 plus E2 bar is the total electric field. And if you integrate this all over the space, you will get total energy. Total energy has three parts, two self energies and one interaction energy. All clear with this? Next one. Yeah, that was a square. Next thing, a cylindrical capacitor. So you construct this by having long coaxial cylinders. Coaxial meaning they have same common axis. Let the radius be R1 and let the radius be R2. So L is much greater than R1, R2, so that I can treat them as infinite cylinders. So if you connect a battery between them, this will acquire a charge of plus lambda, this will acquire a charge of minus lambda, Q will be lambda into L. Do you guys remember the field inside a hollow cylinder? We have done this in Gauss law. So if you see the field inside a hollow cylinder is zero, that means the minus lambda will not create any field inside. And the field outside a hollow cylinder is like a line charge at the center, which that we did in Gauss law. I should check it out in case you forgot. So the field will be given by 2k lambda by R, where R lies between R2 and R1. So there's no field outside and there's no field inside R1. Whatever field is there is only between the shells. Then we can use our potential difference V plus minus V minus integral 2k lambda by R dr. V plus is the final, so R1 to R2 terminals. So this will be 2k lambda ln R, which is ln R2 by R1. This is nothing but potential difference, and that is 1 by 2 pi epsilon, and lambda is nothing but Q by L. So capacitance per unit length is nothing but Q by V. This turns out to be 2 pi epsilon L by ln R2 by R1. So capacitance per unit length, mug up this formula. I have seen this question coming directly a few times, Find the capacitance of a cylindrical capacitor. Done. That is a proper, maybe a bits level question. In cylindrical capacitors, we really don't have much more than this. Energy and all, you can use the same formula, Q square by 2C. Because these are long cylinders, if you take total capacitance, it will tend to infinity because L is very big. So you always say capacitance per unit length. There, those are the three capacitors. For the parallel plates, it was A epsilon by D. For the spherical capacitors, it was 4 pi epsilon R1, R2 by R2 minus R1, this one. Single shell capacitor is this. Cylindrical capacitor is this. Clear with this, have you? Straightforward, just a derivation, the result is important. Any doubts on this? Next one. The next thing, the important one, combination of capacitors. So first thing, series. So when do you say two capacitors are in series? If they have same charge and if they're in the same branch. Now there is one important thing, when the charge distributes on a capacitor, so listen to this carefully. You have to be careful about this. So C1, C2, we have two capacitors. So when you say charge Q is coming through the capacitor, so this Q will come and settle on this plate. We learned in Gauss law, if a plate has plus Q, it will induce a minus Q on the facing plate. But since the plate is neutral, if it becomes suddenly minus Q, that means plus Q charge will go from here. This plus Q will go and get deposited on this plate, and this guy will induce another minus Q here. And because that plate is neutral, because of that minus Q, means plus Q will go from here. So if you see, the charge goes through the capacitor, not by actually going through them, but it is actually by inducing. Think of like, four people. Let's say there are four twins who are playing a relay race. Ever been in a relay race? So what happens? This person goes there, hands over the baton here. This person goes here, hands over the baton. So that is how they run. If all are identical twins, can you tell the difference? For a person who is looking from very far, he will think it's the same person running, isn't it? Whereas in reality, when the it's pass on here, this guy will stop and this guy will start running one at a time. So here, what is happening? It gives you a feeling as if the charge is going through the capacitor, but in reality, charge will never jump across the plates. You're getting what is happening? It induces the charge, and from there, the new charge will go. So technically speaking, this Q and this Q are not the same charge. But then again, we can't differentiate between two electrons, isn't it? So it looks the same. Is that making sense, everyone? Right, Poroja? So that is one important thing. Be careful there. When you say charge going through a capacitor, it doesn't mean charge is actually going between the plates. It is simply being induced. So the charge on the positive plate induces negative charge on facing plate. And plus Q goes ahead. So this is how the charge is flowing from one plate to another plate. But when you see the overall thing, it gives you a feeling the charge is just going through. So remember, charge will never jump across the capacitor. So let the voltage of this capacitor be V1, let the voltage of this capacitor be V2. So you are trying to replace this whole capacitor with one C equivalent whose voltage is V1 plus V2. V1 and V2 are potential difference across the capacitor. So we get from here V1 plus V2 will be V equivalent. We know Q is equal to CV, so this is Q by C1 plus Q by C2 is Q by C equivalent. There. The formula is reverse of resistors, everyone. So capacitors in series will have a formula reverse, like resistors in parallel. So 1 by C equivalent is 1 by C1 plus 1 by C2. Because they have same charge, C1 V1 is C2 V2, the voltage will divide in the ratio of opposite capacitance. So when they're in series, more the capacitance, lesser the voltage across it. Check this out. Clear, everyone? So be careful with that. Series parallel thing can be confusing if there are resistors and capacitors. Sometimes people do goof up. Even I do sometimes, that series parallel, we do some mistakes. So be careful with that. Next thing, what about in parallel? When do you say two capacitors are in parallel? If they have same potential difference? And across same nodes. What do you mean by a node? Node is simply a point where two branches meet. If you think about a tree, right, the point where the new branch appears is a node. But then again, you can take anything there. So this node is a point where branches meet. C1, C2, you are replacing this with one capacitor, C equivalent. Let the charge be Q, and this is Q1 and this is Q2. So we have Q is equal to Q1 plus Q2. Q is nothing but C equivalent into V. They all have same potential difference because they're in parallel. So V at C equivalent is equal to C1 plus C2. Q1 is equal to C1V. Q2 is equal to C2V. So if you divide them, charge will divide in the ratio of C1 is to C2. This is the thing for parallel. There you can see the formulas have completely reversed like for resistors. Clear with this? The next thing. So normally whenever you solve circuits, right, remember there are 5 techniques that we have. One is series parallel, one is Wheatstone bridge, nodal analysis, symmetries, and Kirchhoff's law. We're going to learn these 5 techniques. Out of all of them, most of the times the questions will get over with symmetries or Wheatstone bridge, parallel series, or nodal analysis. If they use Kirchhoff's law, meaning Kirchhoff's law will work, but sometimes it can become very lengthy. We'll see that also. So primarily in today's class and next class, we'll focus on these 5 techniques. And whatever techniques you learn here, we'll use the exact same techniques in current electricity. Only the formula is reversed, but the techniques are the same. So we're not going to repeat them again in current. We'll just do the problems there directly for the circuits part. The next one is your Wheatstone bridge. And this is not a new one. We have already encountered this 2 times. Anyone remember where? The first time you encountered in? Where? Vectors. Heat transfer, conduction. I'm just joking. People are surprised. Second time, where did you encounter? ये याद नहीं रहेगा. फ्लूइड नहीं है, से प्रॉपरली से ना फिजिक्स बोल देना, वो बेटर है ना. कहाँ पे वंश? यू आर देयर. उसमें भी सब पार्ट पॉइजलीज इक्वेशन याद है? We can treat the pipes as resistances. That was the second time you encountered. So Wheatstone bridge. If you have 5 capacitors, C1, C2, C3, C4, and C5. If C1 by C2 becomes equal to C3 by C4, actually what happens is, if you just remove the C5 in the middle and look at it, if C1, C2, and C3, C4 is ratio is same, then A and B will have same potential because they're in series. That is why you can remove C5. If this ratio is not maintained, you can't solve this usually. Normally we have to use Kirchhoff's law. We will see that later on. Your final circuit becomes like this. You can actually extend this. We have something called an extended Wheatstone bridge. If C1 is to C3 is to C5, if C2 is to C4 is to C6, if the entire condition should be satisfied, then C7 and C8 can be removed. Now be careful, if only this condition is satisfied, but C3 by C5, C4 by C6 is not satisfied, then you can't even remove C7 also. Because if you can't remove this, that means C3 will get affected because of C5 and C8. So C1 by C3 won't match with C2 by C4 anymore. So either you remove C7, C8 or you don't remove any one. That is one thing in this extended Wheatstone bridge. You have to satisfy the whole condition. You can't remove only C7 because C2, C1 by C3 is C2 by C4. Because if you don't remove C8, the C5 and C6 will mess up C3 and C4. So it's an extended Wheatstone bridge. You can have any number of layers, but that all that ratio must be maintained. Yeah, the two techniques, series and parallel and Wheatstone. Clear with this? Then let's go ahead with the problem. We have a battery here, capacitance, capacitance, capacitance. This is a conducting wire. Find C equivalent and charges on each capacitor. Think what will that wire do? First thing, what does a wire do? So listen to this carefully. This is important what a wire does. The wire has only one job to do. It's a conducting wire. If you connect a conducting wire between two systems, what does it do? It makes the potential same. That's it. It does that only. It doesn't do anything else. All other things that happen are consequences. So if you take a conducting wire, makes the potential same for the connected nodes. Now, if you take an element like a resistor, capacitor, anything, and now if you put a wire across this, what you did, you made this point and this point the potential same. This phenomenon is called shorting. So if you put a wire across an element, now since the potential difference is zero, the charge on the capacitor is zero. If there is no charge, then capacitor is useless. That means you can just ignore the capacitor. You have to keep it across the element. Now you have to be careful. For example, if someone gives you like this, and now if you put a wire across this, you can't remove these two. Are you getting it? Because when you connect a wire like this, you simply made this point A and this point A, fair enough. This point is not A, this is some other point B, isn't it? The potential difference is not zero across any capacitor. You can't remove any of them. Just because you put a wire, just don't randomly remove anything. You have to be careful. Is it across the element? The potential difference has to become zero. Only then you can remove. Like this, if you connect like this, you can't remove any one. This example. Is that making sense, everyone? Great. Now let's see the question. So that means this guy is gone. This point and this point became same potential. This capacitor, the ones I'm marking in red, are in series, so that is C by 3. This and this are in parallel, that is 2C. So this is C by 3 and this is 3C, and both are in series. So 1 by C equivalent is 1 by C1 plus C2. So C equivalent is C1, C2 by C1 plus C2. That would be C by 1 by 3 plus 3, 3C by 10. Therefore, charge that is flowing will be C equivalent into V, which is 3CV by 10. So charge Q comes out of the battery Q. So this will get Q. This will get Q. So charge Q will split. Both are in parallel. It will split in the ratio of 1:2. So this will be Q by 3 and this will be 2Q by 3. And then Q comes out again. This will become Q. Then Q comes out again. So remember this thing. If a charge Q comes out of the battery, charge Q has to come back to the battery. Tell me one thing. Does battery produce charge? What does a battery do? Battery is like a water pump. It will simply take the water from one here and it is just circulating the water, isn't it? So it is simply taking the charge in the wire and it is continuously pushing it. It is not creating a charge. So if you push a charge Q out, charge Q has to come back from the backside. That is one important feature of a battery. You can't have Q going and Q by 2 coming back. Clear with this thing? Series, parallel, there's nothing hi-fi about this. Anything you're not clear, please ask. The wire thing is important. A wire simply makes the potential same. That's it. If it is across an element, the difference becomes zero. That's why you remove it. Just because there's a wire, don't randomly start removing stuff. That was one important thing about the question. Series parallel is fine. Going ahead, next one. This would be a good one. So in the middle, we have a switch. Find C equivalent before and after closing the switch. This would be a mains question. Second question, how much charge flows through the switch when it is closed? This would be still a mains question, little tougher one. When you close the switch, how much charge went through the switch? Find the heat produced when the switch is closed. So now it becomes an advanced more than one choice question. If they ask you heat, then yeah. Heat when switch is closed. So after closing the switch, how much heat is produced? Let's get them all. C is the main important question. Get A and B. I'll give 2 minutes. Yeah, capacitance is easy. Give me the answer for B. Remember, this is not a Wheatstone bridge. C, 2C, 2C is not even balanced. There is a wire in the middle, so. right home. नहीं por वजह. Did you guys get the first part? C to C to C C. You can clearly see these two are in series and parallel. 2C by 3, 2C by 3. So C equivalent is 4C by 3. The charge flowing through this will be 4CV by 3. Since up and down is symmetrical, this is 4CV by 3. 2CV by 3 and 2CV by 3 will split. This plate will be 2CV by 3. This also will be 2CV by 3. Minus 2CV by 3 minus 2CV by 3. This is how the charges will distribute in the first case when the switch is open. And what is the energy stored in here? The initial energy of the system will be half C equivalent V square. You can just directly do half C equivalent V square. That will be 2CV square by 3. And through the battery, 4CV by 3 charge point. This is the situation when the switch is open. Now, if you close the switch, now think of like this. If this point is A, this entire thing is a wire, so let's call it B, and this point is C. If I just try to redraw this, so this point would be A, and the B, I made it like this. Can I do this? Since this point thing is just a point, I can compress this and I can do whatever I want with this. Now you can suddenly see these two have become parallel, these two have become parallel, and these two are in series. Can you see the whole circuit has got messed up? Previously, it was like series, parallel. Now it was parallel, series. Now if you try to find the C equivalent for this will be 3C and this will be 3C, both are in series. So C equivalent is 3C by 2. The charge has changed. Now the charge flowing through the switch is 3CV by 2. So this will go 3CV by 2. And we know the charges will divide in the ratio Q1 is to Q2 will be C1 is to C2. This will be C by 2C. 1 is to 2 ratio mein charges should divide. So this guy will get CV by 2. This guy will get CV. Now look at what happens here. This will be CV, 3CV by 2. So basically this lower charge will go up, upper charge will come down. You're getting, they'll crisscross. This guy will become CV by 2 and this guy will become CV. So this charges will be CV by 2, CV minus CV by 2 minus CV. And the charge flowing through this will be 3CV by 2. And the final energy will be half C equivalent V square 3CV by square 4. So this is C equivalent and everything. Now, how do you find the charge flowing through the switch? Now, unlike capacitor, right, there is no direct formula like, Q is equal to CV for a wire. So we have to use different techniques. So this was the scenario when the switch was open. Look at this thing. So this was the scenario before. This was the scenario after. Now here, I want you to have a look at something here. Just look at these two plates. I'm marking them in black. So if you just look at the black plates, what was the initial charge on both the black plates? The Q initial was 0. What is the final charge on the black plates? Minus CV by 2 plus CV. So this is CV by 2. So my question is this. Initially you had 0. Out of nowhere, suddenly you got CV by 2. If you observe, these two are isolated, isn't it? There is no way charge can come out of thin air. The only way you could have got charge onto those two plates must be through this switch in the middle. Does that logic making sense? There is no other way. The only way those two plates must have got charge from anywhere, that is the switch is the only inlet for it. That's it. Therefore, charge flowing through the switch is CV by 2. I think that is wrong, right? Then So exam, there'll be two options, CV by 2 going up, CV by 2 coming down. Is that logic making sense? That's how you have to figure it out. See that switch is connected to what systems. Find the charge on that systems before and after. Whatever is the difference must be through the switch only. Any doubts on this? We still have a question, heat produced. How do we do that? Charge total is not same. What are you talking?
So like initially it was 4 CV by 3, now it's 3 CV by 2. Charge total coming out of the means flowing through the whole circuit.
But it is coming back to the battery. What is the problem? Chalo, Bihan, let me ask you. What is the total charge on all the plates?
0. 0.
Yeah. So what is the total charge on all these plates? 0. So what is the problem? The total charge on a capacitor is 0. It doesn't matter. They're just getting redistributed.
Yes, sir.
The charge flowed is right, but 4CV3 went and it came back. So nothing actually went outside. Total is still neutral. Clear with this. Now, what is the heat produced? I taught you this thing in the last class. Remember this formula? Heat produced is the initial energy plus work done by batteries minus final. Now, there is something about the batteries here. Listen carefully. This discussion is important. If you have a battery, V, this is plus and this is minus. So the work done by a battery is given by the charge that flows through the battery into potential difference of the battery. That's your formula, straightforward. So if a charge Q comes out of the battery, so charge is going from here to here, so the charge is being pushed out. So this is battery is getting discharged. The battery is losing energy while pushing the charge out. So battery is actually doing work on the other systems. So work done by the battery is plus Q into V. Same thing, if the charge Q goes into the battery, this is what happens when you charge your mobile. The battery is getting charged. This happens when you have multiple batteries. In this case, battery is absorbing energy. The work done by battery will be minus QV. So it's important you need to see whether the charge went into the battery or came out of the battery. So in our question, initially 4 CV by 3 went, then 3 CV by 2 went. So now remember, the question is heat produced when the switch was closed. So tell me one thing. Let's say, just an example, on the system here, initially there is 100 coulombs. When you close the battery, the charge became 120 coulombs. Does that mean the battery gave fresh 120? It just gave that extra 20, right? So all the charge didn't flow through the battery when you closed it. So the extra charge that flowed through the battery was 4 CV by 3 minus 3 CV by 2. This is CV by 6. Therefore, work done by the battery is CV by 6 into V. CV square by 6. So the heat produced is initial energy plus work done by battery minus E final. The initial energy was this, no, this 2 CV square by 3. Work done by the battery was CV square by 6. Final is minus 3 CV square by 4. How much is this? 5 by 6 minus 3 by 4, 20 minus 18 2 by CV square by 12. That's your heat produced review. That what makes this heat produced in an advanced question. You have to find the equivalent before, after, charge flowing, battery, how much it discharges. You have to do a lot of stuff. Please have a look at the steps. The work done with the battery is an important thing. Any doubts on this? Anyone not convinced with anything particular here, please ask. Next one. Next one. Now, if you see we did nothing here, just series parallel. You can play this much. Now, let's see another technique. Sometimes you'll see circuits like this. So A and B. So battery is connected between A and B. All capacitors are C. So I'm not showing you the battery, but battery will be between A and B. And when you see these kind of questions, right, with wires and all, some potentials are becoming same, and sometimes it is easy to figure out. This is still a little easy to figure out. But sometimes, something is there, but you really can't see it clearly. So we use a technique like this. We call it nodal analysis. So step one, identify how many nodes are there. So listen carefully. I'll show you one method. And then I'll ask you more of something of this sort. It's not tough. It is easy one, but listen carefully. Identify the number of nodes. So this is 1, 2, 3, 4. There are 4 nodes, 4 junctions basically. And check for nodes with same potential. Maybe they're connected with a wire, or maybe there's some kind of symmetry. Sometimes you can see and tell, yeah, these two are looking identical. So figure out if any nodes have same potential. Now I know this point is connected with a wire, so this entire wire must have same potential. So if I call this point A, then this point also must be A. Do you agree? That's what a wire does. If I call this point B, then this entire wire must also be B. So even though for namesake there are 4 nodes, there are only actually 2 different nodes. Step 2, name the nodes. You can use 1, 2, 3, A, B, C, D, whatever you want to use. Step 3, redraw the circuit. Now let's redraw the circuit. So there are 2 points here. So A is the starting point, B is the ending point. Let's number the capacitors. Let's call this capacitor 1, capacitor 2, capacitor 3. Capacitor 1 is between A and B. So put it here. Capacitor 2 is also between A and B. Capacitor 3 is also between A and B. All three are in parallel. Is this making sense? So when you redraw the circuit, suddenly it looks like, okay, you can see what is there. That wires and all will get whole thing entangled. So you just have to be careful. Got the method. This is still an easy one. So you can actually see and figure it out also. But if it becomes a little complex, you have to redraw. All clear with this? Let's see a question like this. Now you guys try. All capacitance are C. Find CAB. Step 1, identify the different nodes. So if this guy is A, this whole thing is A, right? If this is B, that is B. There is no one else. This has to be C, isn't it? This point is nothing. This is not A, this is not B. So it should be something else. So let it be C. That is how you draw. If there is nothing there, that point you can't relate to anything, then it is just a different point. So this whole thing is A. This guy is B. This guy is nothing, so C. And be careful while drawing, right? See, normally I always keep A and B. So A and B will be always in the corner. Remaining points will be in the middle. And while drawing, just be careful. Make sure, the circuits are not crisscrossing like this. So draw in such a way they don't crisscross. So you can arrange the alphabets. So put the alphabets here, A, C, and B. You're done. So let's name the capacitors 1, 2, 3, and 4. So one capacitor is between A and C. Two capacitors also between A and C. Three capacitor is between A and B. Four capacitor is between C and B. And this. Able to see this? These two are in parallel. 2C. 2C by 3. 2C by 3 plus C. 5C by 3. Get the C part. Right side. If this is A, this whole wire is also A. This is B. This is no one C. This is also no one D. So we have four different points A, C, D, and B. So between A and C, there are two capacitors. There's one capacitor between C and D. There's one capacitor between A and D. There's one capacitor between D and B. There's one capacitor between A and B. Total, how many are there? Six capacitors must be there. There are six. This is how the circuit looks. Check. What is the equivalent for this? Get it? Right, Anna. We have two answers for this, everyone. Right, Rihan. Series parallel. The whole circuit has become series parallel. There's nothing there. Anyone else? One more answer. We have three people with the answer. Right, Ishana. Answer is 13C by 8. Check it out, see where it went from. 13C by 8 is the answer. Clear? These two are in parallel, series, parallel, series, parallel. So it's all parallel series only. Clear with this? Let's see one more like this. So there is another way of asking these questions. Let's say we have parallel plates like this. So we have 5 parallel plates. Area A and distance between them is D. Then what you did, you connected these two plates and you connected a battery between these two plates. This is voltage V. So let's call plate 1, plate 2, plate 3, plate 4, and plate 5. Find C equivalent. That is an easy one. And charges on each face of the plate. When I say face, now, so plate 1 has one up, one down, isn't it? There's an upside, downside. Second up, second down. Third up, third down. There are total 10 faces. I want charge on each face. That can be a good question. They'll ask you find the charge on the second plate, find the charge on the fourth plate, find the charge on the third plate downside. Now you can ask a lot of things. C equivalent is a straightforward mains level question. But the moment I ask for charges, it becomes something else. Let's get that. C equivalent. Okay, let's get the charges part. That is what I'm more keen on. Think. I'll give another 2 minutes and I'll show you. How will you get the charges on each face? Let's see. So when you're finding C equivalent only, na, you have to draw it carefully, then you will see the thing. So let's name them only, na, 1 up, 1 down, 2 up, 2 down, 3 up, 3 down, 4 up, 4 down, 5 up, and 5 down. Now tell me one thing, what is a capacitor? Is the plates the capacitor? The space between the plates is a capacitor, isn't it? So there is 1, 2, 3, and 4, isn't it? There are 4 capacitors here. Be careful with that. Plates are not the capacitors. Great. So what are the terminals? So let's call this point A and let's call this point B. This plate will be C. This plate is also C because both are connected by a wire. And this plate is D. So I have only four terminals, A, C, D, and B. Look at the first capacitor. The first capacitor is constructed between A and C. That is between 1D and 2D. So the first plate is connected due to one down and second up. Are you getting this? Next capacitor is between C and D. That is constructed by 2D and 3 up. So 2D and 2U are both C only. Can you see? So if someone asks you find the charge on plate C, you have to say 2U plus 2D ka charge. Is that clear, everyone? Then we have a capacitor between D and B. D and B ka capacitor is 3 down and 4 up. Then we have a capacitor between B and C. This is between 4 down and 5 up. Is this clear? So you name the plates. Which plate is what? Now what is C equivalent? These two are C by 2, parallel, 3C by 2, 3C by 2 and C, 3C by 5, C, C, C by 2, C by 2, C, 3C by 2, 3 by 2 into C by 3 by 2 plus 1, 3C by 5, no? 3C by 5 and charge is equal to 3CV by 5 where C is equal to A epsilon by D. Is this clear, everyone? Now what are the charge distributions? So charge Q will come here. So this will be Q. I'll just redraw this again. Wait. So this charge Q will come here. So this plate will have plus Q. Then Q will continue to go here. Remember, this whole thing was C by 2 and this was C. So charge will split in the ratio of the capacitances. So this guy will be Q by 3 and this guy will be 2Q by 3. Is that clear? So this will be Q by 3. This also will be Q by 3. This will be 2Q by 3. The opposite plates will have negative charge. So this is minus Q. This is minus Q by 3. This is minus Q by 3. And this is minus 2Q by 3. So if someone asks you, find the charge on the second plate, so what should you do? You should add 2U plus 2 down, no? That will be minus 2Q by 3. You're getting it? If I ask you to find the charge on the fourth plate, then I have to do 4U and 4D. Is this making sense? That would be a pretty good question. Find the charge on the second plate, and most people won't understand what do you mean by second plate. You have to take 2U and 2D ka charge, and they both are not equal and opposite. This is how you construct this if I ask you the charge on each face. Any doubt on this? So if they just ask you for C equivalent, right, that will be a little, the decent question, mains level, but if they want to really ask you something more, this is how they will mess it up. Clear? Next one. Find CAB. Look at this in the middle. They're not touching, just jumping over that wire and going. Find CAB. This in the middle, this curve indicates it is jumping over. Some of you are not answering any questions. I know some of you are trying. Some of you are not even trying also. It is a concern. Try. C. Yeah, all are C. Did you guys notice? It's a hidden Wheatstone bridge. If you see carefully, can you notice this? If I remove this guy in the middle, can you see the Wheatstone now? This by this is this by this. You can remove that CD in the middle. Anyways, now if I try to use the nodal analysis, you'll notice something. This is A, this is B, this is C, this is D. Now this is the big clue, okay? If all the points are different and if you redraw the circuit, you're not going to get anything, isn't it? That nodal analysis is pretty useful if you have at least one common point. If you just have all the points different and if you redraw, you're not going to get anything. Yeah, but I can redraw this in a little different way. A, C, I'll just put them in a way you can see them more clearly. See, there's one capacitor between A and C, there's one capacitor between C and D, there's one capacitor between D and B. There is one between A and D, there is one between C and B. There you can clearly see. This is a Wheatstone. And therefore the second one can be removed. So CD can be removed. This is how the circuit becomes. So CAB is equal to C. It's a hidden Wheatstone bridge. What about B? Get that also. This is also Wheatstone bridge. See, this is C and this is D. If you draw them, so you will get a Wheatstone, which is a parallel to one more capacitor between A and B, isn't it? So here also CD can be removed. So this will be 2C. So it's a Wheatstone in parallel with one more capacitor. Able to see this? This capacitor AB will in parallel. That entire thing is a Wheatstone. So generally, Wheatstones, they really can't ask too much variety in this. So these are like Wheatstone. This is your third technique. First was series parallel. Second was nodal analysis. Third was Wheatstone. Out of all the five, the symmetries are the most important ones. Even in symmetries, we have different types: infinite symmetry, axial symmetry, bisector symmetry, cube symmetry, diagonal symmetry. So we have a lot of cases in that. Kirchhoff's law is like brute force. All clear with this? Next one. So whatever I'm teaching you now, if you just replace the capacitor with a resistor, you will get reverse of this answer. You will get R by 2 because series and parallel are opposite. So the same techniques we can use in current electricity. There we will not do these problems. We will do something else. So we got a cube here. A, B, C, D, E, F, G, and H. So each segment is a capacitor. So there are 12 capacitors in total. All RC. Find capacitance between A and G, capacitance between A and B, capacitance between A and C. So if you keep the battery between A and G, what is the capacitance? A and B, what is the capacitance? A and C, what is the capacitance? In a cube, these are the three cases you have. You connect between any two, you will get one of these three cases. Think how will you approach this? Let's go with A and G first. Try for 2 minutes, then I'll show you. Then I'll give you time for AB and AC. Three C near. Let me teach you one technique. Say. So cube, right, is special. It has a certain kind of symmetry. So we are going from A to G. So let me ask you this. If I'm going from A to G, can you give me one path? Right, Vignajit? Shana, some of you got it. Can you give me a path? I can go A, B, C, G, right? Now, if you see, when you're starting from A, there are only three possibilities you can take. You can go A to B, A to D, A to E, isn't it? And observe this clearly, for every path that you take from A to B, A, B, C, G, I can show you a similar path A, D, F, G. I can show a similar path A, E, H, G. Meaning, if I erase these alphabets B, D, and D, if I erase them and if I rotate the cube, you can't tell me who is B, who is D, and who is E. Do you agree with that? So for every path that I can take through B, I can find a similar path through D and similar path through E. That means B and D and E are identical. That means they should have same potential. Getting it? This happens with a cube. So that's your argument. And similarly, C, H, and F are identical when you come from the backside. Is that making sense? So for point G, C, H, F are identical. So for every path from A to G through B, we can find a similar path through D and E. Therefore, point B, point D, and point E are identical. Again, you need to understand the electrons don't care, or the chart doesn't care who is B and who is D. It is your and my imagination. So if there are three identical paths, it's like when you're going from A to B, and if there are three identical paths, equal paths, equal time, they will take equal distribution, it will go. So they will have same potential. Therefore, B, D, E have same potential. Means even if you put a capacitor between B and D, it can remove it. It is useless. Similarly, you can argue with the same thing. C, H, and F are also same. Therefore, even though there are like 8 points, your whole circuit becomes like this. This is point A. You can take B and D and E, you can club all of them together, one single point. You can club C, H, and F together, single point, and you have G. So cube symmetry with a nodal analysis. So each capacitor, I will draw one line. So one line is one capacitor. So between A to B1, three capacitors. B2, there are two capacitors. D say two capacitors. E say two capacitors. Three capacitors. Total 12 capacitors, 12 lines. This is parallel 3C, 6C, and 3C. So CAG will be 6C by 5. Check. So in a cube, this works. Now can you try from A to B? Now you try A, B, and AC. I'll give another 2-3 minutes. But any doubts on this, please ask. So the main thing is to figure out, okay, there are symmetrical paths. And if there are symmetrical paths, matlab, they must be identical. So the potential must be same. So that is the whole thing about symmetries. In all symmetries, you always make an argument somehow that these are same, and then you solve. If this had been resistors, answer would be 5R by 6. It will just reverse. C becomes 1 by R and you'll get the answers. So we're not going to do this thing in resistors. We're going to skip all this stuff there. In current electricity resistors, we have better questions to do. Let's go with for AB and AC. I don't know, Aditya. I should solve. Exam I'll come and tell you, yeah. Exam ask me, I'll come through the window and throw some chitties. Just give me a call in the middle of the exam. Sir, I need help. Current electricity का वो question का चीटी चाहिए. I'll come with an ambulance siren and then try. I give it 2 minutes, not try. Where am I running away? I'll show you the answer anyways. Out of all three, AB is the most messed up one. Try. You need to ask yourself the same question. I want to go from A to B. How many ways can I go? While going like that, Are there any paths which are identical? If they are, then they must be the same. Aditya, we have one answer. Aditya Adalkar. Hope you have solved it instead of remembering the answer. Chalo, good, good. Let's see. So when you go from A to B, you can go directly from A to B. Chalo, that is useless. You can go from AD, CB, you can go AE, HB, isn't it? One is on the floor and one is on the wall. Aren't these two paths identical? So by symmetry, you can clearly see ADCG, AEHG are same. So if you look at this, so point D and point E are identical. Similarly, from backside, point C and point H are identical. Remember, F and G are not same. Think like this. When I go from A to B, A, E, F, G, C, B, right? So F के बाद G आ रहा है ना? If you see, you're not getting equivalent from both the sides. Think of like this. If there are 6 people in a line, if I go 2 inside and 2 inside, do I get the same person? They're not symmetrical. You're getting it? F and G are not same. So be careful with that. So there are actually 6 points. A, D and E are same. F is there. G is there. C and H are same and B is there. Now if you redraw them, each capacitor is a line. So between AD, AE we have 2. DF, EF we have 2. FG there is 1. There is 2. There is 2. D2C we have 1. E2H we have 1. A2B also we have 1. If you actually put 2 horns like this, it looks like a monster. See? If you solve this, I'll give you 30 seconds. Circuit like an egg stuff, and solving this is one thing. It's all series parallel only again. End of the day, it becomes series parallel. So we are using cube symmetry, nodal analysis, and series parallel. Maybe हाँ ये बोल रहा था. There should be 3 numbers. The answer has 3 numbers: 7, 1, and 2. Right, Ishana? Oh, I said 3 numbers. There have 2 answers. Right, Aditya. 12C by 7. How did you get that? Check karo. 2C, 2C. That 2C, 2C becomes C. This is already C. So this whole thing becomes C by 2. This is C. This is C. This whole thing becomes 5C by 2. This is 2C. This is 2C. That becomes C. That C and 5C by 2 will become 5C by 7 plus C, 12C by 7. Be careful that series parallel. how did you get complete reverse of it? Parallel series में सब कर लिया तू पूरा.
नहीं वो लास्ट में पैरेलल को उल्टा नहीं किया.
Next one, question अभी तक हुआ नहीं. AC. What if you connect the battery between A and C? This now later on I'll teach you one more method. It's much easier to solve. Same thing actually, but think for a minute. So these three, right? You connect between any 2 points in a cube. These are the only 3 possibilities you can get. Let me show you something. If I draw a plane here, this now is actually called a bisector symmetry. बाद में we'll have a name for it. Can you see? This is a symmetrical plane. मतलब the left and right side are mirror images. If you see, A and C are mirror images of this. Right? So that means DHFB, if you see, think of like this. If I go from A to C, how can I go? A, D, C. D is the midpoint, agreed? A, B, C, B is the midpoint. A, E, F, G, C, F is the midpoint. A, E, H, G, H is the midpoint. Now you tell me, if you have a circuit, if left side and right side is looking same, and if you have a midpoint, and if this is V and this is 0, what is the potential here? P by 2, right? If left and right are identical, then the midpoint should have half of the potential, isn't it? That means all these 4 points have same potential. So while you go from A to G, so this plane D, F, H, B is symmetrical plane. So when you go from A to C, you will notice D, B, F, H will be midpoints. And left and right are same. If left and right are identical, and if you're a midpoint, means your potential is half. Assuming one is 0 and one is V. It will be VA plus VC by 2 actually. You're done. That means what? Therefore, if they have same potential, you can remove capacitor between. So any capacitor between them can be removed. So capacitor between BH and DF can be removed. Then your circuit looks pretty easy to see. Isn't this how it looks? Now it is easy to solve, no? This will become C, C, that is C by 3, and 3, 4 C by 3. Once you remove those two, your life becomes easy. The entire upper one is in series and up and down are in parallel. That is the thing with symmetries. You have to argue always. This thing we will talk in more detail. There's a name for this thing. We call it a bisector symmetry. So this is cube symmetry. The other 3 cases. Clear with this? There was a question like this. We had a cube. Inside we had one more cube. All these edges are connected. I'm not drawing it properly. This is A, this is G. समझ में पॉइंट कहाँ पे? Inside cube का B था. Each segment is a resistor or each segment is a capacitor. Cube inside a cube, and all these are connected. These are wires, okay? These are wires. Remaining all segments are capacitors. So there was something like that. Did you get the figure? I will leave it here. You can try and see if you get something. I don't think I have a picture. One of your senior asked during the revision. It's a cube inside a cube. So both the cubes are connected by 8 wires to the vertices. And I want you to find the potential difference between this guy. B is this point and A is this point. I think even these are capacitors, I guess. That is actually resistance ka problem. Take it as resistance. All wires have resistance R. Next one. There's a cube inside a cube. Next type of symmetry. Let's say we have a capacitor. We have a capacitor, infinite grid, and so on till infinity. This is C, this is C, this is K times C, this is K times C, this is K square C, this is K square C, and so on. If I just give you everything C, that's a pretty standard question. A proper mains level question came multiple times. This is a little variation of it. Find CAB. K is some positive constant. So the capacitance for each branch is getting multiplied by K. Aditya, that's not the answer. What's the catch? See, these kind of questions, one thing you must have understood. Let the whole thing be X, and we remove one branch, isn't it? Let CB be equal to X. If everything had been C, your life would have been easy, isn't it? If everything was C, then you could have called this thing is also X, isn't it? If everything was C, if you remove one branch, it is still X only. Now, my question is this: whatever answer that you will get, C, A, B, it will be proportional to capacitance, isn't it? Dimensions, right? Units and dimensions. It will be some constant into C. So CAB will be proportional to C. Now, what you're doing here, this entire infinite grid, you're replacing C with KC. So what do you think will happen? And if it is proportional to C, you're replacing C with KC. So this entire infinite circuit is similar to where C is replaced by C, replaced by KC. Therefore, this entire section must be K into X. Does that make sense? If the whole thing was X and you started your first circuit with C, if I replace Kc is equal to C dash, then this will be C dash, Kc dash, Kc dash, isn't it? Then shouldn't this whole circuit isn't looking like the same thing? But C ka place mein C dash tha. Therefore, that CAB must be proportional to C dash, but C dash is nothing but Kc. Therefore, this is Kx, isn't it? Logic समझ में आ रहा है? C को simply Kc से replace कर लिया. So your final answer instead of X it must be Kx. That is the catch in this thing. So if you replace that with K there, the whole thing becomes Kx. And then you're done. Redraw the circuit again. So we have C here, we have C here, and this whole infinite grid that you replaced will be Kx. So CAB will be Kx and C are in parallel. So Kx plus C into C by Kx plus C plus C. But remember, this whole thing is again equal to X, isn't it? This whole thing must be again equal to CAB, which is nothing but X. You'll get a quadratic from here. Kxc plus C square is equal to Kx square plus 2Cx. Kx square plus X into Kc minus 2C plus C square is equal to 0. Solve this, you'll get X answer from here. Other steps clear, everyone? If you put K is equal to 1, that will become your regular circuit. Everyone got the logic there? If you multiply only the upper part with K, then I don't think you have any symmetry there. You can't, then it doesn't look the same. Then we have to try something else. This symmetry though won't work. We have to see something else. Maybe we can use some kind of a nodal analysis or something. We'll see. Let all the techniques get over, then we'll see maybe we can do something. But it won't be symmetrical. No? The thing is, if I cut it, it should look identical. Now in infinite grids, we have another variety. This is a good one. This is an infinite grid. Each segment is a capacitor. There are infinite capacitors. Capacitor, capacitor, capacitor. Ever-ending capacitors. So in this, we have a point A here. We have a point B here. All are C. Find CAB. Infinity में is another variety. Think for a minute. There is a way to handle this kind of things. You should have seen the technique before. I'll show you one and then I'll ask you another variation of this. Hmm. Let's see. Listen to this thing. So we use something called principle of superposition, and we have used it multiple times if you remember. First time we used it in projectile motion. If you split the motion along x and y axis, whatever happens in x doesn't affect y, and whatever happens in y doesn't affect x. So I can treat them as two independent things. Now, this infinity is a special thing. What we will do, first consider only point A is there and assume B is not there. Consider only point A. And let's say if I push charge Q through point A, by symmetry, what do you think will happen? Every side is uniform, so it will split equally in all directions, Q by 4, Q by 4. So if there are capacitors, okay, I'm not drawing them, Q by 4. So if you push charge Q through point A, right, the charges will distribute Q by 4 and the charges will keep on splitting, and they will go to infinity. So meaning the second terminal is at infinity. You're getting it? These charges will keep on spreading till infinity. And the battery is connected at infinity, so charge will come back from there. So assume only A exists. And let charge Q go inside. And goes to infinity. Okay. Plus, now let's say A doesn't exist, only B is there. This was B. So B used to be here, okay? And I won't name it, but B used to be there. A used to be here. Now, pull charge Q out of B. Pull the charge Q out of the B. Then what do you think will happen? That means the positive terminal is at infinity. The charges will come Q by 4, Q by 4, Q by 4, and Q by 4. Same way we are doing it in the reverse. Assume only B exists. And let charge Q come out of point B. Now, by symmetry, when you connect a battery, what you're doing basically, you're giving and taking the charge, right? If I do both at the same time, what do you think will happen? If I push the charge Q from A, and if I pull the charge Q from point B, just look at the branch between them. This plus Q charge will push Q by 4. and this B ka charge will also push Q by 4. Means if only A was there in that branch, you would have got Q by 4. If only B was there in that branch, you would have got Q by 4. Since A and B are two independent things, if I push and pull the charge at the same time in that middle branch, connecting the capacitor between A and B, you should have a charge of Q by 2 and minus Q by 2. Is that making sense? Is this argument clear, everyone? Then we know capacitance is nothing but charge by potential difference, right? So we can clearly see here VA minus VB is equal to Q by 2C. So Q by potential difference is 2C. Therefore, CAB is 2C. This entire infinite grid is just equivalent to a 2C capacitor. You're getting this thing? So when I push the charge without B being there, the system doesn't care, right? Tell me one thing, does the circuit care whether there's a battery or someone is just pushing the charge inside? System doesn't know no, what kind of charge is coming. If only A sends the charge, that branch would have Q by 4. If only B sends the charge, you would have got Q by 4 again. If both are happening at the same time, you should get Q by 2. So if you just overlap both the circuits now, you'll get that only. This is a very interesting technique. You will later on see, for example, see. Let's say we have a circuit here. Let's put some resistors. Resistor here, and let's say resistor here, and we have a battery like this. Let's say V1 and V2. So what you can do, you can remove the battery V2 and replace it with a wire. Then remove the battery V1 and replace with a wire. And let's say V1 gives you current I1 in this branch and V2 gives current and I2 in this branch. If both the batteries are there, you'll get current I1 plus I2 in the middle branch. Because one battery doesn't care what the other guy is doing. They both will try to push the current, and if they'll just add up normally. Is that making sense? Assume only V1 is there, find the current. Assume V2 is there, find the current. Put both of them, the current will add up in that branch. This is what I mean by principle of superposition. If two independent events are happening, and if they produce effect 1 plus effect 2, if both act at the same time, you'll get effect 1 plus 2. We have seen this in NLM also. If you had force F1, mass M1, acceleration A1. If you had force F2, mass M, and acceleration A2. If you apply F1 and F2 together, you'll get acceleration A1 plus A2 factorially. Clear with this? Everyone got the idea for this? The infinite grid. So you guys do this thing. I'll give you something similar. Instead of a grid, what if I have a infinite honeycomb? Ever seen a honeybee's nest? Hexagons going infinity. Each segment is a capacitor. I can put a resistor also. Story is the same in resistor. Let's say this is point A and this is point B. I will do one thing, wait. Find CAC and find CAB. CAC is easy. CAB is fun. 3c by 2. Same story. If you send, I don't remember the answers. देखना पड़ेगा. 3q by 2. q कहाँ से आया रे? कैपेसिटेंस तो पूछ रहा हूँ. तेरे तो अलग ही लेवल आंसर्स आते हैं. 3c by 2. ओके. ये AC है क्या? I think that looks like everything. AB भी निकालो सब लोग. I don't remember the answer. I need to check. Okay. Most people are getting 3c by 2, I guess, for the first one. Let's say you push the charge only through A. Wait a second. So if you push charge Q here, it will go symmetrically Q by 3, Q by 3, Q by 3. Remember, C is sitting here. We will not write it. This is C here. If you pull charge Q here, Q by 3, Q by 3, Q by 3. This was A here. So when you do both at the same time, this guy is pushing Q by 3, and this guy is also pushing Q by 3. So the capacitor between A and C will have 2Q by 3 minus 2Q by 3. So VA minus VC, potential difference is 2Q by 3C. So C equivalent is nothing but charge sent through the battery by potential difference, 3C by 2. Clear? Same thing if I do for AB. So if you send Q now, this will be Q by 3, this will be Q by 6 and Q by 6, isn't it? देखो ना, once you come here Q by 3, there are only two ways you can go. It will split further. And both the paths are identical. That Q by 3 doesn't know which way to go, so both will look same. It will split. So we need to go to this guy here, B. Same argument if I do this. So if I pull Q from here, this guy will be Q by 3 and this will be Q by 6. And this was A. So if you draw the capacitors between A, there are two capacitors between A and B. And the charge that is going is Q by 3 plus Q by 6. So between A and B, so this is pushing Q by 3. This is pushing Q by 6. This is pushing Q by 6 and this is pushing Q by 3. Net, they both are pushing Q by 2 each. So this will be Q by 2 minus Q by 2, Q by 2 minus Q by 2. This is A and B. Making sense? So what is the potential difference? So if I just take this point C here, so VA minus VB is the potential difference between them. Potential difference is what? Charge by capacitance, Q by 2C plus Q by 2C, which is Q by C. C equivalent is charge by VA minus VB, which is C. Is this clear, everyone? So if you get infinite grids, this is the way to do. You start with one point and push the charge and pull the charge. Same thing you do in current electricity also. Clear? Yeah, that is one thing about infinite grids. We still have more variations of this. Next thing is actual symmetry and bisector symmetry. That is little big. We should do it when you're fresh. Okay, that was the last one for the day. We will wind up with that. Make sure to go through this. This is a pretty good one. You can try and tell me what you got. I don't remember the answer. It's a good one. Okay, with that we'll wrap up for the day. So we have done almost 17 questions. Do make sure to go through them and do finish your electrostatics, Gauss law and gravitation ka solving. Some of you didn't complete it, so do finish it off. Pretty important topics. Okay, and yeah, next week a test is online. You have time till Thursday again, so make sure to give it. Any doubts, anything you have, so you can stay back and ask, or else you're free to leave. I'll see you guys again on Monday, as usual, same time.